Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Let's suppose we have a function z equals f of xy. And that function f of xy is continuous and differentiable across some region. Let's also suppose that we take a slice at some point on the z-axis and parallel to the xy plane, such that f of xy is equal to a constant c. To visualize this, let's look at a function in 3 dimensions. So z equals x squared multiplied by y is described in 3 dimensions by the blue region shown here. And so f of xy in this case is x squared multiplied by y. If we now take a slice parallel to the xy plane at some point, so in this case z equals 3, you'll see that we're left with flat curves on the xy plane. And this is the type of solution we find when we solve an exact differential equation. Function f in this instance is known as the potential function. We know that the total derivative of f is given by the formula df equals the partial derivative of f with respect to x multiplied by dx plus the partial derivative of f with respect to y multiplied by dy. And if the function f is equal to a constant, then its total differential equals 0, as the derivative of a constant is always 0. Let's now say we have a function m of xy, which is equal to the partial derivative of f with respect to x, and a function n of xy, which is equal to the partial derivative of f with respect to y. If we substitute functions m and n into this equation here, we get that the total derivative, df, is equal to the function m multiplied by dx plus the function n multiplied by dy, and this is equal to 0, as f of xy is equal to a constant c, and the derivative of constant is 0. In solving exact differential equations, we're going to start with the differential equation in this form and find a solution to it which is in this form. So how then do we know that a differential equation is exact? Well, firstly, we know that it's a function of x and y multiplied by dx plus a function of x and y multiplied by dy, which is equal to 0. Next, we can use the fact that if a function f of xy is continuous and differentiable across a region, then the mixed partial derivatives must be equal. What this means is that the partial derivative of f with respect to x and then with respect to y is equal to the partial derivative of f with respect to y and then with respect to x. Now, we know that the partial derivative of f with respect to x is the function m, and we know that the partial derivative of f with respect to y is equal to the function n, and therefore the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So in this type of differential equation where m dx plus n dy is equal to 0, if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, the differential equation is said to be exact. And we can use techniques for solving exact differential equations, which we'll come on to in the next video. So for now, let's look at some potential exact differential equations and test to see if they are exact. So let's start with the differential equation 2xy dx plus x squared dy is equal to 0. The first thing to observe is that it appears to be in the correct form for an exact differential equation. So m dx plus n dy is equal to 0. So m in this case is 2xy and n is equal to x squared. If we now take the partial derivative of m with respect to y, which means holding the x variables constant, it evaluates to 2x. If we take the partial derivative of n with respect to x, so this means holding the y variables constant, we see it also evaluates to 2x. So the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. The differential equation is therefore said to be an exact differential equation. And in our next example, we have differential equation 2xy minus sine x dx plus x squared minus cos y dy is equal to 0. At first glance, it looks like it's in the correct format, so we have a function multiplied by dx plus another function multiplied by dy is equal to 0. So let's test the mixed partial derivatives. So in this case, our function m is equal to 2xy minus sine x, and our function n is equal to x squared minus cos y. So taking the partial derivative of m with respect to y, so that means holding the x variables constant, it evaluates to 2x. And taking the partial derivative of n with respect to x, so that means holding the y variables constant, this also evaluates to 2x. And so the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So in this case, the differential equation is said to be exact.